Hello, and in this video we're going to be looking at three basic transformations of exponential graphs. We'll look at these individually and then maybe sketch a few that have a combination of the three together. Alright, the first transformation that we'll be looking at is the vertical stretch or compression. That's going to be by this a value that's in front. So if this a value is greater than 1, it's going to be a stretch. If it's between 0 and 1, it's going to be a compression. And if it's negative, then it's going to be an x-axis reflection. Okay, so if we had, for example, the functions f of x equals 2 to the x, and f of x, or g of x, equals 3 times 2 to the x. This would be a vertical. So if I graph the first graph, we'd be at, so I'm going to put this one in green. It's going to be right here, here. So it's going to look like this. It's going to cross at 1. It's going to go through 2 here. And then it will be 4 and 8, because it's doubling each time. 4 is doubled to 8. Okay, so this is f of x. Okay, and it keeps going this way, and it stays on the axis. Now, g of x, which is a vertical stretch, means that we pull it away from the x-axis by a factor of 3 here. So this factor of 1/2 at -1 would be multiplied by 3, so it would be up here. Oops. It would be up here. Okay, this number is also called the y-intercept, so it's going to cross at 3. 1, 2, 3. It's going to cross at 3 because it usually crosses at 1. Right? Our intercept here on every one without an a value is 0, 1. Now this is our intercept. Y-intercept. Okay, that value of a is the y-intercept, so this is going to be, in this case, it's going to be 0, 3 as our y-intercept. Okay, now this point, which is 2, would be multiplied by a factor of 3, so that would go up to 6. 3, 4, 5, 6. This one is 4. It would be multiplied by 3. That would be 12. That would be up here. So it stretches the graph out to a multiple of 3 times as much. It's still going to come down here. It's still going to approach 0. But it's going to be stretched vertically. Now, if we had a factor that was less than that, okay, so if we had a factor that's less than that, we created a function here called h of x, and its factor is 1/3 the original function. That would be the y-intercept. Okay, and so we'd have a 1/3 down here as a graph. This 1 value would be, our 2 value would be 2/3. So this value right here would be 1, 2/3, because normally it's up 2, but we're taking a third of that. And then 2 would be 4/3, because it would be reduced by a third, and that's 4 up here in the original graph. So it's compressed on the axis. It's a little shorter. It's compressed. That's smaller than the original graph. So that's a vertical stretch compression. Now, if we also had a function that's opposite of that, so if we just did, let's say, a function L of x, and we just did a negative times -1 times 2 of x. So that's going to take this green function and it's just going to reflect it. So the reflection of that graph is going to be I'm going to use this color down here. So instead of 1, it's going to be at -1. It's going to reflect. So it's going to look like this. Here it would be, instead of 2, it would be -2. So it's going to go down like this. This would be the function right there of -1 times 2 to the x. It just reflects it on the x-axis, on this x-axis here. So anytime we have a negative number. Now if we had like a -3 times 2, it would create this blue graph, but it would be reflected down here. So instead of 3 up here, it would be -3 down here. So they'd be reflected afterwards. So you do the stretch first, and then you do the reflection next. So after when you're building the function. All right. Now the other two types of shifts are going to be horizontal and vertical shifts. So this was our only stretch or compression. Now we're going to do shifting. So we're going to, if we did this function here, this is going to be a shift or right or left. So if we say, for example, f of x equals 3 times x minus 2, that would shift right 2 units. So our regular function, 3 to the x, would go through here, would go through 3, then it would go through 9. So it would look like this. This is f of x, or g of x, equals 3 to the x. Now this one would shift right 2 units. That means everything would be shifted over right 2 units. This one here, it's at 3, would be shifted over right 2 units. This one would be shifted over right 2 units. This one would be shifted over right 2 units. So it's the same type of graph. It's just shifted over to the right. So it looks like that. Okay. It would have the same long end run problems. That means as you go left, it's going to go to negative. As it goes to negative infinity, it's going to go to 0, and as it goes to positive infinity, it's going to go to positive infinity. Right, the intercepts will change because we've shifted right 2 units. Okay, now if we had the problem f of x equals 3 to the x plus 5, that would shift left 5 units. So in a horizontal shift, it shifts the reverse of what the value, positive or negative value is here. Okay, that's shifting right or left. Now the vertical shift is just when you add something to the end. So vertical shift, add some value to the end here. We shift up or down. This is up or down. Okay, so an example of that would be f of x equals 3 to the x plus 5. Okay, so that plus 5 is not up here with the x, it's just afterwards. So the 3 to the x function, we'd have 3 here, we have 9 there, we have 1 there. So this is regular 3 to the x, approaches the axis here. Okay, this one right here with the 3 to the x plus 5, we shift this up to 5, or from 1 to 2, 3, 4, 5, 6. Shift it up to 6. It shifts the horizontal asymptote. Okay, so on these they have a horizontal asymptote. This has a horizontal asymptote of 0. Y equals 0 is a horizontal asymptote. It would move it up to 5. move that up to 5, y equals 5. Y equals 5 is my horizontal asymptote. It would just shift everything up 5 units, so it would go like this. And so this would be 8. So go right here, like this. So this would be our f of x function with the 3x plus 5. This would be just g of x equals 3 to the x power. Okay, so it shifts up 5. And to shift it down, we would put a negative there. So if we gave you an example of f of x equals 3 to the x minus 2, that would shift the y values down 2 units. We just shift the y values, not the x values. All right, so this changes the horizontal asymptote. Okay, these up here do not change the horizontal asymptote. Horizontal asymptote is the y-axis here. The horizontal asymptote is the y-axis, is the x-axis. I made a mistake. Is the x-axis. The x-axis, or y equals 0, x-axis, is the horizontal asymptote. And it doesn't change unless you shift it vertically, up or down. You shift it up or down, then it's going to be that. Now, the other thing in this section that wasn't really talked about in any of these graphs was our growth factor. So growth factor in a problem, so this is something that's not the same as a graph, but the growth factor is how we change the base. Okay, so this is the base. Okay, we're looking at the base. And we're determining what it is above 1 or 100%. So a factor that's, if we have this equals 2 to the x, then this factor of 2 is actually 1 more. 1 plus 1 is 2, so this is 1 more. That's going to be 100% more than the one that is in the base. So this is 100% growth. We also consider it doubling because it's 2 instead of 1. All right. Usually a growth factor is something that's less than 100%, but it can be more than. In this case, it's exactly 100%. So if we had a function of 1.23 to the x, then that means we have 1 plus 0.23. That means we have 20.23 growth factor, which is equal to 23% growth factor. So we're looking at a percent above the 100 if we're doing growth. If we're doing decay, then we're looking for a number under 1. Okay, we'll talk about that in the next video.